So it's 11:50 and we're going to start our math interest group presentation. Our speaker for today for the math interest group is Jim Landwehr, who's giving a talk on Simpson's paradox. The topic and choice of the speaker involved a bit of serendipity. I had come across an article that showed the data for a fully vaccinated group of people had a surprisingly large number of reinfections with the Delta variant. The efficacy of the Pfizer mRNA vaccine for COVID was called into question. Subsequently, another article cited the Simpson's paradox as the cause for misinterpreting the data. So what is the Simpson paradox? I'd never heard of this before. So I suggested this topic to Jim Landwehr, who graciously accepted to give this talk. And we're lucky to have him as a statistician in our OGARD and the MIG group to do so. Jim has worked for Avaya Labs in Basking Ridge, and I found out that he has taught statistics, which included Simpson's paradox. So who better to educate us on this topic? So please welcome Jim in giving this premier talk for MIG on the Simpson's paradox.
Okay, thanks, Walt. Let me share my screen here, make sure that's working. So I have an abstract up there now. Can you see it and hear me?
Yes,
okay?
we can. Yes, we can.
Okay, great. Well, like Walt said, Simpson's paradox is one of those statistics topics that it does come up occasionally in the real world, and it's kind of confusing, and it always seems to be confusing. But so what this talk really is three examples going through it in the details, and in some detail, and with real numbers and real examples, and hopefully give everybody a little bit of insight into what's going on. And please stop me anywhere and ask a question. So if people can unmute themselves, if people are set up so that they can unmute themselves and ask a question whenever appropriate, that would be fine with me. So there's an abstract here. It just says that basically Simpson's paradox is kind of a confusing topic, and it's interesting, and it comes up in the real world. So it's about, maybe I was thinking it's about as far as from Jerry Eisenberg's talk right now as you can get, except that actually the first example is a sports example. So here's the situation. In 1995, a certain baseball player had a higher batting average than Derek Jeter. We all know Derek Jeter, right? And in 1996, that same player also had a higher batting average than Derek Jeter did in 1996. So therefore, you would think that considering both years together, that player would have a higher batting average than Derek Jeter, right? That seems plausible. If the guy's got a higher average in year one and he's got a higher average in year two, you might think, well, he's got a higher average. So let's look at the data. This is all real data in this talk today. And let's see what's happening. So here we are in 95. Derek Jeter had 12 hits in 48 at bats, and the batting average is the hits over total at bats. So its batting average was 250. And David Justice, the other player who was with Atlanta, but not as famous as Derek Jeter, he had 104 hits over 411 at bats. So his batting average was 253. Okay, now let's look in 1996. Well, Derek Jeter had 183 hits over 582 at bats, so he had 314. David Justice had 45 hits over 140 at bats, so he had 321. So in 1996, David Justice hit 321, Derek Jeter hit 314, Justice had the higher average. In 95, Justice hit 253, Jeter hit 250, so Justice had the higher average. But now the question is, well, what if we look at both years together? So we're going to look at the results marginally over both years. That was, we're just going to consider both years together as this set of data. So we then a look at 95 and 96 together. So Jeter had 48 at bats in the 95, 582 in 96. So Jeter's total at bats would be 630, and Jeter's total hits would be 12 plus 183 over 195. So these are just straightforward calculations. So Derek Jeter's batting average over the 2 years together is 195 hits over 630 at bats. So he hit 310. Justice, if we look at his total things, he had that many 411 hits in 95 at bats in 95, 140 at bats in 96, so 551 total. And his number of hits is 104 plus 45, 149. So, and sorry, this thing keeps coming up on my my Adobe screen, but it goes away, I guess. So Justice average over the 2 years considered together was 270. So who had the higher batting average over these 2 years together? Well, Derek Jeter did. So what's going on? Seems counterintuitive. Justice hit better in 95, Justice hit better in 96. Considering 95 and 96 together, Jeter hit better. Well, this is an example of Simpson's paradox, and it's kind of like the is as simple of an example of Simpson's paradox as I have come across, and easy to understand. Does anybody want to hazard an opinion as to sort of why this happens here? Or do you follow me? First, that you see that there's just really these three tables that have all the data that we're talking about here. And Jim Blinn, I could see you have raised your hand.
Yeah, it looks like we have a situation about sample size that would play out because you've got so many fewer at bats by Jeter in 1 year and Justice in the next. It turned out that when you did the combination, you got the results the way you did.
That's right. It's not that I did. This is the way the data is. So this is real data. Obviously, I got it from somewhere, but I didn't make anything up. I haven't made up anything.
I didn't mean that. I just
meant that's right. So that's right. In 96, both players had higher averages, but Jeter had a lot more at bats in 96 than Justice did. And in 95, both players had lower averages, and Jeter had a lot less hits than Justice did. So if we're looking at the average over both years, basically Jeter's average is going to weight the year 96 higher when actually both of them had higher batting averages. And Justice's average over the 2 years is going to weight 95 when he had the higher average. So that's basically what's going on here. And if you look at it that way, okay, it makes sense. It's not necessarily a paradox, but this is a pretty simple situation. And so now I want to move on to a second situation, which is a sort of a classic example. It's in, it's made its way into many statistics books, and you find it a bunch of places. So here, again, real example. In the early 1970s, the University of California at Berkeley was sued, or maybe they were about to be sued, for gender bias for graduate school admissions. And the graduate school at Berkeley obtained the following admissions data for fall of 73. So for men, there were 8,442 applicants, and 44% of the men were admitted. For women, there were 4,321 applicants, and 35% were admitted. So there were a substantially bigger percentage of the men were admitted than women. And the sample sizes are pretty big. So this is not just a small sample variation by chance. So this is something that looks substantial, and Berkeley was worried about getting sued or about to get sued because of this big disparity. Well, as many of us know, the universities don't like to get sued, especially for something like discrimination. So they looked into it, and they had they appointed they had some statisticians and also a dean, and the statisticians involved actually ended up being a dean in the longer run. And this was an interesting part of his career. So they decided, well, people are admitted to departments, so let's look at the data by department and see which departments seem to be having the problem and what's going on. So let's look at it in more detail. And so here's the data for the 6 largest departments. It's not every department in the school, but 6 largest departments. So let's look at what's going on here. Well, Department A, 62% of the men were admitted, but 82% of the women were admitted. So it doesn't look like Department A is causing the problem. Department B, 63% of the men were admitted, but 68% of the women were admitted. So it doesn't look like Department B is causing the problem. Department C, 37% of the men, 34% of the women. Well, a little bit higher men are admitted, but not a big difference. D, 33% of men, 35% of women. Again, women are a little bit higher, not a big difference. E, 28 and 24. The men are a little bit higher, but not much of a difference. F, 6% and 7%. F has got very low admission percentage to both for both men and women. So what's going on here? What's the explanation? Anybody want to add a comment? Well, what's happening is that the women are applying to departments that have higher admission standard, that are admitting fewer people. So if we look at the men here, the department that the highest number of men have applied to is 825 here, Department A, and that is admitting a relatively large percent, both for men and even more so for women. But if we look at the women applicants, women are applying, their biggest department is applying to C, where the admissions are quite a bit smaller, in the mid-30s. And now if we look at the department where the second highest for the women is this one E here, that's 393 for the women, and it's a small percentage, a much smaller percentage getting admitted. And then for the third one here, it's a very small percentage, Department F. So what's happening here is that there are relatively small differences between the admission rates for men and women within each of these departments, but there are large differences in admission rates between departments. So the women were tending to apply to very competitive departments with low rates of admissions, which they said Department C was English, and departments A and B, where the men were applying most, were engineering and chemistry, I think is what it said. So the women were applying more to departments with low admission rates, and the men were applying to departments more with high admission rates. So the overall admittance rate for women is lower than for men, even though there's not a substantial difference or a statistically significant difference in that, for that matter, in any of the specifics departments. So are you with me with that? Is there any comment or question? So what do we make out of this? Well, in this particular analysis here, it would say make sense to think about it as conditional on the department, because students are admitted by the department. They're not admitted overall by the whole school. So we don't want to look at things marginally across departments. We want to look at things conditionally on the departments in this particular problem. For the baseball example, you might say, well, if we want to know whether one of these hitters is better than the other overall in terms of their batting average, maybe we would, if we're thinking about the overall hitting ability, for that particular problem, it might make sense to ignore the year and look at the overall results marginally across the 2 years. So the point is that based on the specific problems and what we're interested and what we're trying to do or trying to learn about, sometimes we might want to look at things conditionally, and sometimes we might want to look at things marginally. Okay, are you with me?
Yeah.
So there's some terminology that's used for these type of situations. So I just want to give you a little of the terminology and then how it fits into these two examples. So we have a response variable, a Y, and in the first one, it's hits. The players get hits or they make outs. The second one, it's admission. They either get admitted or they don't. Then we have an explanatory variable, X. The first one, it's the player, it's Jeter or Justice. We want to, and the second one, it's the gender of the applicant, male or female. But then we have this control variable called Z. It's a third variable. In the first example, it's the year, 95 or 96. In the second, it's the department, the different department name. And then the question is, what's the comparison of interest in these problems? In the first one, it's a proportion. It's the batting average. We want to consider the proportion of hits either in each year or overall. And the second one, it's also a proportion. It's the admission rate in to the graduate school. So in looking at problems, in my mind, it helps to think in terms of these concepts. What's the response? What's the explanatory variable that you're mainly interested in? What's the control variable Z that might have an impact? And then what's the measure that you're interested in looking at? And what's the statistical comparison of interest? So we'll go through that now more extensively in a recent COVID example. But first, though, a little bit more on the terminology. The Z variables can go by many years, many names. It could be called control variable, like I put there. It could be called a stratification variable, could be called a confounding variable or a concomitant variable or a lurking variable. And there's other terms too. I kind of like the term lurking variable because it's the idea is that there's a variable lurking in the background, like the department that maybe you don't think about in the first place, but it could have an effect on the results. The other terms are, you see all of these terms in all sorts of literature. They're all, at least at this level, pretty much have the same meaning. Like I said, I kind of like the phrase lurking variable.
Jim,
Yeah.
How is the lurking variable compared to the hidden variable that we hear about in statistics?
Well, I think it's the same thing. A hidden variable, a lurking variable. I'm not quite sure, but I would say it's probably the same thing.
Well, I was thinking of Einstein calling quantum mechanics incomplete.
Well,
And then there's this big debate of there are no hidden variables, at least according to Bell.
well, I'm not going to be able to get into quantum mechanics, but if in quantum mechanics there is some variable that that nobody had thought of, like the hand of God or something or other like that, well, then maybe that's lurking. But this is much more down to earth, more maybe real isn't quite the right word, but more straightforward than anything involving quantum mechanics. So a hidden variable to me would just mean a variable that might be there that you don't know about, or maybe you know about it, but you don't have the data on it. So these are all different terms that have more or less the same meaning. And also notice that I haven't done any modeling, no fancy calculations. This is all just numbers and looking at the numbers this way, that way, or the other way. So there's no modeling in either these two examples or the third example that we're going to get into in a minute. So hopefully that helps, Al, but hidden variable, I would say, is just one more term that I could put in here in the same spirit. So what is Simpson's paradox in this framework? Well, Simpson's paradox is the result that the marginal association between X and Y, the relationship between X and Y, can have a different direction from the conditional association or the conditional relationship between X and Y given Z. So how does that relate to these examples? So if we took at the graduate school at Berkeley admission, well, the relationship between X and Y is marginally is that men have a higher admission ratio, whatever it was, 44% to 35%, but conditional on department, there's really no difference. In the first example, the marginal relationship between X and Y, considering both years, was that Jeter had a substantially bigger batting average, but the conditional relationship between X and Y in each of these years was that Justice had a slightly higher batting average in each of these years. So this, in the terminology, this is the way I would describe Simpson's paradox in terms of these examples, in terms of this terminology. And now what I want to do is go into a little bit longer example that was referred to by Walt in his introduction, that's sort of motivating, or at least it shows this topic keeps coming up in the real world all the time. Sometimes it's recognized, sometimes it's not. So any other questions or comments before we go into this COVID example? Okay, if you raise your hand, I can't see everybody, but I think if you raise your virtual hand, go to the top of my Zoom screen here and I would see it. Okay, so let's move on. This example is something I've extracted from a blog site that's called COVID-19 Data Science, which is written by the person who's the department head director of Biostat at the biostatistics at the School of Medicine at University of Pennsylvania. There's a reference link there, and there's also some links at the end of the talk, at the end of these slides. So this is from his September 9th or September 20th entry, and it uses data that he downloaded from the Israel Ministry of Health, covering a period from August 10th to September 8th. So let me go here. So it turns out that Israel has electronic health records for everybody in their population. And so they have very good population-wide health data, and they evidently post some of it on their websites. And this was a topic that has been in the news and does keep coming up in the news all the time. So let's look at this data from sort of a step through some several steps with it. So these are Israel deaths from COVID during this period. And this particular example uses data that Jeffrey Morris downloaded and put in his blog. So the total number of deaths in Israel from COVID during this period was, where's my mouth? It was 277 deaths of non-vaccinated people. Sorry about that. 307 deaths of people who had been vaccinated, fully vaccinated, but hadn't received the booster shot at that time, and 83 deaths of people who had been fully vaccinated and received the booster. So there were a total of 667 total deaths, the sum of those three numbers. So there were 667 deaths from COVID in Israel during this 30-day period. And of these deaths, 307 plus 83, which is about 58%, were fully vaccinated or fully vaccinated and also boosted. So what we see is that about 60% of the deaths in Israel during this period were people who were fully vaccinated or fully vaccinated and boosted. So a natural question is, well, if 60% of the deaths are people who are vaccinated, is the vaccine really working or not in terms of reducing deaths? Maybe maybe it's just recently in New Mexico were vaccinated. It was I can't remember, I was just eating breakfast and it came across the radio, but looking at the percentage of people who died who were vaccinated, that's just not that's not going to be relevant to answer any question about whether the vaccine is working or not, because we also need to know what percentage of the population was vaccinated or not. Okay. And as I said, this initial misinterpretation of data keeps coming up. I believe that's what I heard this morning. Okay, so let's go on. Since Israel has these very good health records, Morris was able to get data. And now, we can look at the numbers in the population that were in each of these three categories. So in particular, of the Israel population, according to Morris, found that 3,456,060 were not vaccinated. The number that were vaccinated was 4,446,000, and the number that were vaccinated, this VAX-NB means fully vaccinated but not boosted, and then the 1,200,000 were vaccinated and boosted. And so roughly 62% of the population was at least fully vaccinated, 40% vaccinated, not boosted, and 13% boosted. Now, I should say that this is data that's from the blog and that Morris has a number of footnotes. The top versions of these charts, the last one and the next several, is I've just copied from his blog. And he has a number of footnotes about details of the data, exactly how he handled this and that, but I don't want to go into that for the purpose here, which is to illustrate how Simpson's paradox comes about. But of course, it is important to be careful with the data. So what we need to do is to calculate the death rates, or the death rates per 100,000 population, for each of these three groups, the non-vaccinated, the vaccinated, not boosted, and the boosted. So for the boosted, the death rate during this period is 83 deaths divided by the population, 1,200,310 times 100,000 to make it a number per 100K. So for the boosted, the death rate was 6.91. For the vaccinated, not boosted, going through the same thing, 307 divided by 4,446,000, et cetera, got 6.90 per 100,000. And the death rate for the not vaccinated is 277 divided by 3,456,000, et cetera, 8.01. So those are the three death rates. These are death rates for these three separate populations of Israel during this month. So what do we see from this? Well, we see that the Well, no, I first just say these are the death rates from the population. These are not the death rates for people that got COVID. That would be a different concept. It's called a case fatality rate. That's not what this is. So what we see here is that the death rate for the non-vaccinated group, 8.01 per 100,000, is a little bit higher, somewhat higher than the death rate for each of the two vaccinated groups, which is around 6.9. So now what we want to have as a measure here that's relevant for this problem is a measure of vaccine effectiveness. And the way to do that is to look at the death rate for a vaccinated group compared to the death rate for the non-vaccinated group. So how much the effectiveness of the vaccine has to do with how much the death rate is reduced. And again, note here the data, the outcome is death rate. We could have had different outcomes: hospitalization, serious disease, symptomatic disease, all sorts of different outcome variables. But this example, death rate is clearly an important outcome variable, and that's the only one that's considered in this talk today. So the vaccine effectiveness for the boosted group would be 1 minus the death rate for the boosted group divided by the death rate for the non-vaccinated group, because we want to look at the death, how much the death rate from the non-vaccinated group is reduced when compared, how much the death rate for the boosted group is reduced relative to the non-vaccinated group. So the vaccine effectiveness for the boosted group is, from these numbers here, 1 minus 6.91 per 100K divided by 8.01 per 100K. That's 0.137 or 13.7%. And the vaccine effectiveness for the vaccinated but non-boosted group is calculated using the same formula with different variables in it. It turns out to be almost exactly the same number. So now we can put these numbers in the table, and we get the next version of this table. Okay, so this is the table that we had before, but now the death rates are added in here for each of these things, and then each of these three groups, and then the vaccine effectiveness for these two groups is put down here, 13.7%, and maybe one should have been 13.9, but they're both about 14%. So what is this saying? This is saying that considering all the people in Israel, or the whole population, considering all the deaths they had from COVID for that month, and using their electronic health records, which is about as complete data as is available, I think, in any country, the vaccine effectiveness was about 14% in terms of reducing the death rate for the vaccinated people, whether they were boosted or non-boosted. In both cases, it was about 14%. Well, and this is calculated marginally using all the data. We've used all the data here. There's no, all the data that was available. So a vaccine effectiveness of 14%, well, that's better than nothing. But what were we hoping for when the vaccines came out in the first place? Well, when they talked about those clinical trials a year ago, and granted, those trials didn't have death rate as the outcome. It had a much earlier, something about symptomatic disease and serious disease and so on, but they're talking about, 90%. And so here we have a calculation that shows that the vaccine effectiveness is 14%, and it's using all the data from Israel, all the deaths, all the population, and so on. So this doesn't look so good for the vaccine. But this is not the whole story. And that's why we're continuing, and that's why the example is here. So age is a possibly confounding variable here, a lurking variable, a stratification variable, confounding variable, control variable. I think you could call it a hidden variable too, because it wasn't included in the data that has been presented so far. However, we know from the real world that COVID is more deadly for older people. So it makes sense to see how age, to bring age into the analysis in some way. Now, since Israel has these electronic health data and so on, age is in there. So Morris is able to get age for all the people in Israel, and as a first cut, he divides the population into two groups: those who are less than 60 and those who are greater than 60. I'm not sure what he did with those who are exactly 60, but at any event, he divides it into two groups: younger than 60 and over for 60, and then he goes through and performs the same calculations on each of these two groups. And that gives us the following table. So the first part of this, all ages, that's what we've got up till now. Those are numbers are just repeated here. And then he divides the deaths into those who are less than 60 and greater than 60. And you see for the boosted thing, there was one death less than 60, and 82 of the 83 deaths were greater than 60 in age group. For the vaccinated non-boosted, it's 9 and 298. Those add up to 307. For the non-vaccinated group, it's 23 and 254. And so all those numbers add up as they should for the deaths. For the actual population sizes, the numbers here are close. They don't quite add up perfectly for reasons that he mentions in the footnote. And of course, population sizes change over time and that, but it's the point is that these numbers add up close enough so that we can go ahead with the analysis here. So what do we see from this data here, where we're looking at it at the things let's first now look at the death rates for the over 60 and less than 60 groups. Well, we see the death rate for the older than 60 for each of these. The death rates for the older 60 than 60 are quite a bit higher: 161, 51, and 10 per 100,000 for each of these groups than the death rates for the less than 60 group. So indeed, people older than 60 were dying from COVID during this period at a much higher rate in Israel than people under than 60. And the death rates are those black numbers there, the numbers in black that were calculated the same as before. We also see that the death rates for just from looking at these numbers, the death rates for the vaccinated not boosted group, 51 and 10 for the over and 60, are quite a bit less than the death rates for the non-vaccinated group. So you see 51 and 10 are quite a bit less than 161. For the lower than 60, it's also the case. The death rates 0.23 and 0.26 are quite a bit lower than the death rate of 0.27. So we see two things here. Within each age group, the death rate is apparently lower for the two vaccinated groups, and there's a huge difference in death rates between the older than 60 and younger than 60 group. So I put that sort of the style of this presentation, as you can see, as I sort of have the words, the numbers are there, and then in the bottom part of each of these pages are the words highlighting what seem to be the important points. Now, another point, though, is that the vaccination rates are different between the two age groups. So if we look at the over 60 group, 53%, there's 52.6 there, is boosted, but only of the less than 60 group, only 5% is boosted. On the other hand, of the non-vaccinated people, 10% are over 60. No, excuse me, 10% of the people over 60 are not vaccinated, and 44% of the people under 60 are not vaccinated. So there's also a difference in the vaccination status of the two groups here. So I've written that down. So the point of this, that age definitely seems to be related really to both X and Y in this case. So we need to have age in some way in the analysis. So what we'll do is to simply calculate this vaccine effectiveness in the same way that we have before, previously using all the data, everybody in Israel, and now we do it separately for those over 60 and those under 60. So are you with me?
Yes.
Questions? Okay, no questions. So we do the same calculation we just did, but now we do it separately for those over 60 and under 60. So the numbers here are the same as before, except this vaccine effectiveness is added in here, and that's calculated for each of these rows exactly the same as we calculated it for the all ages a few slides back. So what is this saying? It says that conditionally for those people who are over 60, that is conditional on your being over 60, the vaccine effectiveness is either 68% if you're fully vaccinated, up to 98%, 94% if you're boosted. The vaccine effectiveness is about 68% or higher. For those who are under 60, looking at only the data for those who are under 60, the vaccine effectiveness is also in the mid 60s, 66%, 63%. So the death rate for those under 60 has also in the mid 60s. And the vaccine effectiveness is in the mid 60s. So let's try to write this. I try to write this as in two sentences. Conditionally using data for those over 60, the vaccine effectiveness is at least 68% in terms of reducing the death rate relative to the death rate for those not vaccinated. Conditionally using data for only those less than 60, the vaccine effectiveness is around 66%, 66, 63, whatever. So how does this relate to you? Well, or to anybody. If your age is greater than 60, then the first statement is relevant for you. And the vaccine effectiveness is around 65% or higher. If your age is less than 60, the second statement is relevant for you. In either case, the vaccine reduces the death rate relative to your situation by about 66% or more. But we already saw a couple pages ago that from the top line of the table, that if we ignore age and just use the analysis, all the data, the same deaths, the same population, ignore age, we found a vaccine effectiveness about 14%. So whether you are over 60 or whether you are under 60, the vaccine effectiveness that applies to you from the conditional analysis is around 66%. But if you just ignore age entirely, you would say that the vaccine effectiveness for everybody is 14%. Well, this is the paradox. This is Simpson's paradox, in a situation that actually caused quite a bit of press when this came out, and this, not this specific blog example, but this type of data and these results. So it does seem like a paradox. If you're over 60, well, the vaccine effectiveness is about 65% or higher. If you're less than 60, the vaccine effectiveness is about 65% or higher. So that's what it is, looking at that data. But if you ignore age, you come up with a result of only 14% effectiveness. So essentially what's going on here is that the data are saying that the COVID is more deadly for the older group, and also that the older group is more likely to be vaccinated. But for each group, there's a substantial reduction in the death rates for the unvaccinated for the death rates for the vaccinated populations relative to those who are non-vaccinated. So age is a confounding variable here that needs to be included in the analysis. Questions, comments?
Yeah, I have one.
Yeah,
First of all, I mean, this presentation is just terrific, and it's been extremely clear. It's hard to absorb, because there's a lot coming at us, and that's why there haven't been very many questions so far. We're using, we're mostly non-statisticians, and we're learning new terminology and everything. I just want to mention that there was other news. This was a month or two ago from Israel, from that data. And it was concerning whether the boosters reduced the severity of disease.
Yeah.
And I didn't pay a whole lot of attention to it, but my impression is that what happened was they had a guy from Israel testifying in Congress about this, or testifying, maybe it was hearings at the CDC or something. And he was saying how effective the boosters were. I hope I'm getting this right. But the catch was that he was talking about preventing serious disease, enough disease to go to the hospital. And it turns out that if you get sick in Israel with COVID, if you have substantial symptoms, you go to the hospital. In America, if you get sick with COVID, mostly they tell you to stay home until you have a crisis. So you don't go to the hospital until it's an emergency. And so it turns out that that was the hidden variable there. The standard for what it means to be seriously ill was different in the two countries. And so you couldn't make a direct comparison of statistics. You had to put that, somehow divide people in some way, maybe by their symptoms or something, in order to disclose what was really going on.
So my comment on that is that I don't remember the specifics of it. There's been all sorts of versions of this type of data and these issues. It's obviously important to everybody, and it's been in the news. And I have one more example from these data that I'll show in the next slide or two, but that the key thing you're talking about is the endpoint. Here, the endpoint is death. That's pretty clear. If you say the endpoint is severe disease, then you get into the question, well, how do you measure severity of disease? And are you measuring it in the same way everywhere, and so on? So there's no end of details and care that has to be used when the data really matter. Now I see there's a couple other hands, but let me, and I want to have some discussion. Let me just go on, though, to the last part of the example with these data, and then maybe turn to the.
Can we answer one question from the chat room.
Okay,
Um,
I don't see that. I don't have the chat open.
Yeah, okay. This question is from Bill Heary. And this question is, are the deaths from Israel all the deaths from COVID or
During
all
this period.
deaths?
During this period, yes. That's the.
Or are they deaths from COVID or are they all deaths? I guess deaths from all
No, deaths
causes.
from COVID. Deaths from COVID.
Okay, deaths from COVID. Okay, so we have a couple of hands, but we'll wait till the end of the discussion, at the end of the
Yeah,
presentation.
Yeah, so these are deaths from COVID in Israel during this period. And they know that because they have good healthcare records, the electronic records and so on. So this is the Simpson's paradox is very apparent from this, really the 3 lines in this table. But this is not all the story for this data here, because the reality is that children were not even eligible to be vaccinated during this period. And so children, and moreover, it's kind of known that the children, the disease has not been as severe in children. So it makes sense in looking at these data, forgetting about these different endpoints, severity, and or going from Israel to the US or anything else, just in terms of these data, it makes sense to separate out those aged less than 12 from the rest of the group that's less than 60. So basically we go through, or he goes through, which makes a lot of sense. The first line is all ages. That the first row, that's the same as what we've had. No, I take that back. The bottom row, greater than 60, is the same as what we've had all along. The second row, less than 12, so that's the children who, none of whom could be vaccinated during that time. And apparently there were no deaths in that group either. And the population of the children is 2,229,000 and so on. And then that leaves the group that's from 12 to 60. So here we then, we do exactly the same calculations as before. So basically what we've done, or what Morris did, was to separate out the people from 12 to 60 from those who are over 60. And you see the vaccine effectiveness for the last row, well, that's the same as what we had before, 68% and 93.8%. See, that's what we had before because that group hasn't changed. But this less than 60 group has now been divided into 2 sets. There's the children, for which we don't have any measure of vaccine effectiveness. Sorry about that. I clicked on something I didn't mean to. I guess the chat came up. There is no vaccine effectiveness for the children. And then for the 12 to 60 group, we see a vaccine effectiveness of about, for those who are not boosted, of about 90%, and for those who are, or say 89%, and for those boosted, about 88%. So, so this is like, I would say, the end of the story with these specific data available for analysis. And you see that one of the reasons that they initially said, well, people over 60 should be boosted, but not necessarily everybody who got it before, is that the effectiveness of the vaccine in Israel at that time was about 88, 90% for both those who were fully vaccinated, not boosted, and those who were fully vaccinated and boosted. So this is one of the reasons that this sort of data is one of the reasons that they said, well, maybe initially we don't have to boost everybody. So the booster seems to have an impact for those greater than 60, but not necessarily an impact for those less from 12 to 60. Sorry, my phone is going off here. So So let me make a couple comments here. This is using age as a confounding variable, a control variable, a lurking variable. Are there other maybe variables that should also be brought into the analysis or that could be? Well, the answer is yes, if relevant data can be obtained. And possible variables that might be included are gender, male and female. I've seen some stories saying that males have worse results than females. Comorbidities of various health conditions, including maybe whether the person had already had COVID, various socioeconomic status and ethnicity, others. So this is not intended to be the full, complete analysis for the Israeli data for this period of time, but is an example of how Simpson's paradox can occur, does occur, and is understandable, I hope. So if there were more variables coming in, then there would be a more complicated analysis, and the Simpson's paradox type of effect can still occur. And of course, as things get more complicated, it's more complicated to interpret it. I just have, let me just give you my summary here, and then we can go to the questions. So Simpson's paradox is the result that the marginal association between two variables, X and Y, can have a different direction from the conditional association between X and Y, given some confounding or stratification variable Z. It can occur in the real world, as shown by these examples. It doesn't always occur. Substantively, sort of technically, the situation can occur when either X or Y or both is related to Z. That gets, there's various technical analysis that can go on as you get into this topic, but that's the basic result. This situation can occur with discrete or continuous variables. Here, everything is discrete. It's easier to think about and follow through the calculations. How do we deal with this in practice for real problems? Well, my view is it is difficult. There's no simple one size fits all. We always have to just ask ourselves, could there be a lurking variable that the Z that would change the apparent initial association between the X and Y? And if we do find one, is it relevant for our understanding, interpretation of the problem, or as maybe we want to look at things marginally? Sometimes we want to do one, sometimes the other. And a little phrase I like, statistics is data in context. So let's move on to questions. In my thing, it says Mitch is at the top. So
Okay,
or you want to handle the questions, Walt?
I'll handle the questions. We have 1, 2, 3, 4, 5, 6 raised hands. Okay, and let me look at the chat box for a second. Okay.
I also should say I do have a page. Walt can distribute this later, but I have a couple of references with links and comments.
Okay, so the first hand raised is Mitch Erickson. Would you please unmute yourself?
Okay, hey, thanks a lot, Jim. This is a fascinating topic, and I'm reminded of, this is attributed to Mark Twain as well as many other people, lies, damn lies, and statistics. And, obviously, one can cherry pick the statistics one wants to make the story that one wants to convey. And if I were a statistician with very low scruples, I'd hire myself out to the highest bidder on any kind of a political issue, whether it's COVID or abortion or whatever, and proceed to, use this particular Simpson's paradox to prove a point that whichever side hired me would prove that the statistics show that my position is correct. It just, and I hate to be that pessimistic about it, but it sure seems like, there's a lot of ways you can well, just to stay with the COVID, you can prove that that vaccination doesn't, in the statistics you just showed, vaccination isn't worth the effort, or vaccination is absolutely worth the effort.
So my view is that if you look at it carefully and understand the kind of things that go on, that can go on with data, that it's not a question of, you can prove anything. Here, you have to use age. If you're just using the data that ignores age, you either have to use age or you have to say, we need to use age and something else, and if you just ignore age, you're ignoring the heart of the data and you're coming up with a wrong conclusion. So it may be numerically calculated correctly, the 14% and so on, but it's not relevant for our interpretation of the problem. And the idea is that this is the way, Simpson's paradigm, this is the sort of thing that can occur, and it does occur. And the way to deal with it isn't to say that you can prove anything with statistics. It's the way to deal with it is to understand what's going on with the data, decide what view is relevant for your particular problem, whether it's the Derek Jeter overall batting average or conditionally based on your age and so on, and then proceed. But you're right, and that's part of the reason that statistics has a bad name in many situations, because people say lies, damn lies, or statistics, and you can prove anything with statistics and so on. So the statisticians would not, no reputable statistician having seen this thing would argue that the vaccine effectiveness is truly 14% in terms of these data, and this endpoint.
Okay. Let's go on to the next person. The next person is Jim Blinn. Please unmute yourself.
Okay, yeah, Jim, it was a superb presentation. I just really enjoyed it. I may be a little bit biased having a statistics background, but it still was just, I thought you did a really nice job. So thank you so much.
Thanks.
Yeah, I think the key is knowing or thinking to look deeper than the first level analysis. And so you really need people to say, okay, well, let's, we got that 14% number looking at everything all together, but is there anything else that could be coming into play? And of course, with COVID, I think enough people sort of have heard, well, how bad the death rate is among the older people. So that became something that people were willing to look at. But with many statistics presentations you might hear about data, you may not know enough to quickly think about, well, what are the lurking variables? And so really rely on some smart people to start taking that second step and trying to tease more information out. So thanks again.
My reaction is it's substantive knowledge about the problem area and the data and what's important. There's no substitute for that. And just blind numerical calculations can't replace substantive knowledge about the problems.
Okay, let's go to the next question. Ed Atkin.
Jim, very fascinating talk. I was in Israel when I was 13. Did your study include just Israelis or the Palestinians or everybody?
It's whatever is presented by the Israel Ministry of Health. So I would have to, the blog that's referenced there, he's the guy that did this, and so I don't know the details of the Israel health system, but it's whatever Israel Ministry of Health presents. That's where the data came from.
Have you been to Israel, Jim, at all, or no?
No, never.
They have an excellent hospital.
But I did actually I've worked with Israeli statisticians various times over the years, and they're smart people. Just
Thank,
But this is an example. The point is the Simpson's paradox in a current, interesting, important area. I put at the end there, this is not meant to be the be all end all analysis of COVID data or even this COVID data.
Okay, let's go to the next question. Al Aho.
So a great presentation, Jim. And I've seen instances of Simpson's paradox in a number of situations. There's another famous example on restaurant ratings. But you scared me when you said that we need substantive understanding in order to know what's going on. How do we get substantive understanding about what's going on with COVID? What can we believe?
Well, what I really meant is it's not just somebody doing numerical calculations. It's a collaboration with medical people, public health people, people that understand the disease, people that understand what, like Ed's question, what data was really in here. Did it include Palestinians or not? Or people, Palestinian population in Israel. So only that, knowing about the problem, the substance of the problem, statistics. I had the little phrase in there, statistics is data in context, when various times in my career when I'd be doing presentations about statistics to a non-statistical audience, why I always tried to emphasize that. It's not just numbers, it's numbers and context. And the context is the problem. And,
Would error bounds of some kind help in our understanding?
Well, I stayed away from that in this because the basic paradox, the basic problems doesn't have anything to do with sampling or errors. These are population numbers. And, things get more confusing with error bounds and so on, but there's the only error here is if the underlying data was obtained accurately or not.
Okay, thank you.
Okay, let's go to the next question. Rich Jager. Please unmute yourself.
Yeah, great presentation, Jim. As an actuary, perhaps I had a head start over some of the people. We're a little bit familiar with the kind of thing you're talking about. Think of automobile insurance, and the accident frequency is not just the overall population, but as everybody knows, young people have different accident frequencies, and married males are better than unmarried males. So, but great. What might be a little peripheral to the question of the paradox, but I think in the 12 to 60 group, the number of deaths were in the single digits, and so that would raise a question in my mind about how credible the actual rates are for that segment, and whether you had any thoughts about that.
Well, I would say that's, with a smaller number of deaths, there's more variability in the rates, as you know, and error bounds like Alice is talking about, all that come into play, and you don't want to just look at 1 month's worth of data. You want to look at more months' data and see how much these things vary over time and all that. So I guess in my mind, I just tried to provide as simple and as clean an example of what can go on for the Simpson's paradox as I could come across. So yeah, with the rates being small, why they could easily fluctuate on a relative basis more from month to month. And also even with the less than 12 children, apparently there were no deaths during this period, but we have certainly heard in this country about children dying at a low rate, but it does happen. So just because the number is 0 doesn't mean that the true rate is 0 too. So, yeah, and this can come up, I'm sure that this sort of thing can come up in many cases in insurance situations.
But great presentation. Super.
Thanks.
Okay, do we have any other questions from the audience? I like to just make one comment. I had given a talk in February 2020, which related to what China was experienced before it really spread to the rest of the world. And their data, just looking at age groups, was that the death rate between 10 and 60 was less than 1%. And from 60 to 85, it was monotonically increasing from 1 to 15%. I suppose if we take the Israeli data and break it down into finer grain, it would show that, like from 60 to 65, 65 to 70, so on, it'd probably show even better effectiveness for the vaccine than just lumping 60 to and higher. The other might be, the China data didn't look at comorbidities, which are likely to increase with increasing age. If they also broke it down by, people that had organ transplants and take immune suppressant drugs, or just had immune system problems, and also do it by comorbidities, I think it would be a very interesting analysis, which I guess can't be done at the moment because they don't have the data broken down finely enough. But anyway.
Well, the big picture is that that's what the people analyzing data like this as part of their paid job have to do. Or when the FDA reviews these studies, they want to look at any possible lurking variables that are around there that might be related to the study and say, well, have you looked at it this way, that way, the other way, or have you looked at these things together? So that gets into the more, as in any field, there's the easier, things can get more complicated as you get deeper into it. And that's the case here too. But if you really wanted to analyze, these are Israeli data, and the guy Morris in his blog gives references to some Israeli researchers that have analyzed these data or similar data, using more of these potential confounding variables than just age, and trying to get a more of a holistic picture. But I think it's worth realizing that effects like this Simpson's paradox can occur in even, it is basically the same as the baseball example. You're looking at things that get weighted in different ways, and sometimes it's harder to figure out than others.
Okay, do we have any more questions from the audience? Okay, I want to thank Jim for giving us a very clear understanding of Simpson's paradox and an enlightening talk on this relevant subject. And then I'd like to close the big session for today. Thank you.